So here we're looking at satellites, and it is another topic under circular motion, because when we look at satellites we look at firstly the main body, which is a larger body, and smaller bodies that orbit the larger body, and there is an attraction, a force towards the center of the larger body, and this is caused by gravity. For example, if you have the Earth, which has a certain mass, and this is a satellite, could be the moon or any satellite, right? So if you say it's the moon, for example, or any like it could be a rock that's orbiting the Earth. The force, the circular motion, the force due to circular motion is due to gravity. So in this case, the force towards the center of the Earth would be equal to the mass of the moon times its gravitational acceleration, or what's called gravitational field strength. Right, so G is the thing that we need to calculate. So for and the G is not one figure, right? But depending on what the major body is and what the distance between the major body and the satellite, the gravitational field strength or gravitational acceleration is going to be different. And I'm just going to show you how to calculate that. So G stands for gravitational field strength. In terms of newtons per kilogram, and sometimes it's called gravitational acceleration, or it can be called gravitational acceleration. Yeah, it's gravitational acceleration. And to show you how to calculate that gravitational acceleration or gravitational field strength for any satellite that's going around a major body. So what field strength does it feel? And there's this equation. The equation is G, gravitational field strength, is equal to large G, which is the universal gravitational constant, and it has a figure. I'll write that figure down in a minute, times the mass of the major body, which is the larger body. In this case, if we're dealing with the Earth, we need the mass of the Earth. So it is the mass of the larger body, not the mass of the smaller body. It's important to understand. And another thing to understand is R is the radius from the center of the Earth, or from the center of the major body to the satellite. So we know that that the gravitational acceleration close to the surface of the Earth. So a person who's, for example, here, who's on the surface of the Earth, the radius that we have to use is equal to the radius of the Earth, because he's at the surface of the Earth. The further you go away from the larger body, you can see that the radius increases. If the radius increases, that means the gravitational field strength decreases as you go further away from the major body. Right, so let's take the example of a body that's right on the surface of the Earth, or just above the surface of the Earth, a rock or something falling to the Earth. So to calculate that, we know from doing previous problems that G, close to the surface of the Earth, is approximately 9.81. So let's check that figure. Right. So the universal gravitational field. So the universal gravitational constant is, let's write down what that is. It's the universal gravitational constant, and that is equal to, then the second line, quite a big number. With another colour. Right, it's equal to 6.67 times 10 to the neg 11, so it's actually quite a small number. Newtons meters squared per kilogram squared. Right, and to just do this problem here, we need to know what the radius of the Earth and the mass of the Earth is. Right, so we're going to determine the G close to the surface of the Earth, and we should get 9.81. So the mass of the Earth, if we can get that from our textbook, and I've got the textbook opened up. Right, so the mass of the Earth here is 5.98 times 10 to the 24. Write that down. So 5.98 times 10 to the 24 kilograms. And we need the radius of the Earth. So the radius of the Earth, again, we get it from the table. The radius of the Earth is equal to 6.38 times 10 to the 6 meters. 6.38 times 10 to the 6 meters. And so we can put that into the formula. So G is equal to the universal gravitational constant, 6.67 times 10 to the negative 11. Right, times the mass of the Earth, 5.98 times 10 to the 24, and R squared 6.38 times 10 to the 6 squared. Right, we can cancel some things here. Right, so this can cancel, so 24 minus 11 gives you 13, 10 to the 13, and we have here 10 to the 6 times 2 is 12, so that can cancel with this, and we have one more 10 to the 1 left over. So just simplify the calculation a little bit before we put it into the calculator. Sometimes it's a good idea to do that. Okay, saves less, you'll make less errors. Times 10 over 6.38 squared. Right, so now we can use our calculator. Right, so what do we have again? 6.67 times 5.98. 6.67 times 5.98 times 10 over 6.38. And by entering the enter key, we should get a value of 9.81. Let's see what happens. Enter key. Oh, 9.8 is close enough. So we get a value of 9.8, and sometimes we use 9.8. Right, so that is the gravitational field strength, or the gravitational acceleration close to the surface of the Earth. Of course, it will be different for bodies which are further out, and it depends on the major body. The major body could be, for example, Saturn or Jupiter or the Sun itself. So it depends on the major body and how far the satellites are from the major body. So let's have a look. Actually, before we do some examples, when we're dealing with satellites, we have two other values to deal with, or what's called they're two constants, right? For satellites going around a common large body, these two equations, which I'm going to write down, are a constant for each of the satellites that are orbiting that body. So these are the two equations. So these two values remain constant at all times, right? For satellites going around a common body. So I just write that down here. Yeah, so for satellites going around, or orbiting is a better word, orbiting a common large body, the above equations, formulas remain or give the same value, i.e. they remain constant, i.e. they remain constant. Now if you want to know how to derive these, we can actually derive these two equations. Right, so if we're looking at a large body M and a smaller body, a small m. Right, and we know that the is undergoing gravity, so the force towards the center of the larger body is equal to mg, and we said before that g is equal to large g times large M over r squared. Now remember, r squared is the radius to the, r is to the radius to the satellite. Right, it is from the center of the large body. It is not from the circumference of the large body to the satellite. It's actually from the center of the large body to whereabouts the satellite is. Right, so we can equate, in this case, if G equals large G times large M over R squared, then mg is going to be equal to, the G, will just change the G to, all we're doing here is changing the G to large G large M over R squared, and becomes large G large M small m over R squared. So small m is the mass of the smaller body, large M is the mass of the large body, large G is the universal gravitational constant, and R is the radius from the center of the large body to the satellite. Right, now we know that this mg is equal to mg, remember the F net for bodies that are undergoing circular motion is equal to m times acceleration, and acceleration is equal to the tangential velocity over squared over r. And r, again, r is the radius from the center of the larger body to the satellite. Now if we said that it takes a certain time for the satellite to go around, orbit the larger body once, this we call the period, or the time taken. The time taken to go around once, to make one revolution, is called the period. So I'll just write that here. The time taken to make one revolution is called the period, and it's given the letter T for period. So that means we know that velocity is equal to distance, or in this case distance over time. And since the motion is circular, so one circle, the circumference of one circle is equal to 2 pi r, and if we let the time in this case be one period, it's equal to t. So if we substitute this, v equals 2 pi r over t, the period, into this formula. This is the general formula for circular motion. So the general formula of circular motion is mv squared over r. We use that all the time. So here I will substitute the value of v, which is 2 pi r over t, into here. So that means I'll get 2 pi r over t squared over r. And you can see the r's firstly will cancel. And before I do that, just expand the brackets. I got m 4 pi squared r squared over t squared over r. Make sure you write your r's properly, don't make them look like a v. So just cancel here, so this r cancels with one of the r's here. So we were left with m 4 pi squared r over t squared. Right, so if we equate that to this equation here, okay, big G, big M, little m over r squared, big G, big M, little m over r squared is equal to little m 4 pi squared r over t squared, and we just rearrange the formulas. The m here will cancel that m. We can bring the 4 pi squared to one side, so gm over 4 pi squared, and we can bring the r term together, group the r terms together, so you get r cubed over t squared, and we can see that it's the same as the formula we have here. Right. Exactly the same. Right, so those two figures, values, for satellites going around a common body, right, and that's all I've done here, is just show you how to get those two equations, but the main thing is how to use these two equations. And so let's have a look at a question involving the use of this equation, and just generally how to use to deal with questions involving satellites. Okay, let's have a look at a question involving satellite question. Okay, in this question we are going to use those two constants to show you how these two constants work. Just copy down the problem. Okay, we have a space shuttle orbiting the Earth, and the shuttle itself is a satellite. It orbits the Earth once every 93 minutes. This gives you the period of the space shuttle at a height of 400 kilometers above the surface of the Earth. It deploys a new 800 kilogram satellite that is to orbit a further 200 kilometers away from the Earth. Okay, this graph here shows the gravitational field strength of an object which is at a distance away from the Earth. Closer to the Earth, the gravitational field strength is stronger, so we know it's about 9.8 when at the surface of the Earth, but as you go further away from the surface of the Earth, the strength, gravitational field strength decreases. So question 3a is asking us to use this graph here to estimate the work needed to deploy the satellite from the shuttle. So we're going to draw a picture of this. What's happening? It's you have the Earth, you have the shuttle, and then you have it deploys a satellite a little bit further out. So the shuttle itself is at 400 kilometers, and the satellite, this is the satellite here, is another 200k away from the shuttle. Right, so the work done in this case, basically the work done is going to be equal to the potential energy needed to get it up to that height. Right, so we have a mass of 800, we know the mass of the satellite. The G, we need to calculate the G, or read the G off from this graph. Right, so the shuttle now is at 600 kilometers away from the Earth, and so we read it up from the graph. It will have a gravitational field strength experience a gravitational field strength of approximately 8.2. So the further away you come away from the Earth, the less the strength is. So here, so G is approximately 8.2, and the height will be equal to 600 kilometers. So it's 600 times 10 to the 5 meters, or 6 times 10 to the 5 meters. Put that in the calculator. Mass of 800, G of 8.2, and a height of 6 times 10 to the 5. And okay, now that's not the right answer. The reason why is I have used the wrong height. I've used the right height of 6. It should actually be, it should have been the height of 2. Right, that should have been 2. It's a mistake because we're going up just to 200 kilometers, not 600 kilometers. So change that to 2 instead of 6. And go back to the calculator. Right, so it should have been 800. But divide this by 3, it's the same thing. Anyway, put it in again. 8.2 times 2 times 10 to the power 5, and that's the right answer, is 1.31 times 10 to the 9. 1.31 times 10 to the 9 joules. Okay, those who have this question in their books, you can check the answers and you'll find it's the right answer. B. Okay, B. Use the mass and radius of the Earth to assist you in determining the period of the new satellite. So here we get a chance to use this formula. Gm, universal gravitational constant, mass of the Earth in this case. M is the mass of the large body, over 4 pi squared, and R in this case is going to be the radius at which the satellite will be, and then the period will calculate. So we'll use that formula. So it's Gm over 4 pi squared is equal to R cubed over the period. So we can just rearrange this formula so to make the period the subject, and we will get 4 pi squared R cubed on Gm. So now we just put the figures into the formula. Now we need to get the value of G and the value of M and the value of R. Now I wrote that down before. Just the value of R, we don't know. Maybe I'll write that down already. It's up here somewhere. Okay, yes, okay. So we have those values. I'll just copy these values down. the side so I can see them. They're out the way. Right, put those values in. So it's 4 pi squared. R in this case is going to be 6 point. R of the Earth is 6.38. The satellite is at 6 times 10 to the 5. 6 times 10 to the 5 meters away. So this is 6.38 times 10 to the 6 meters away. So if I add this to the radius of the Earth, right, it will become 6.98 times 10 to the 6 meters. Cubed. And G .67 times 10 to the negative 11, mass of the Earth 5.98 times 10 to the 24. And before I put that in the calculator, I just do some cancelling. Can cancel that with this, becomes 13. And this is 10 to the power 18. 10 to the power 18. Right. I can cancel that with this, so that cancels and it becomes 10 to the power 5. So 18 minus 13 gives you 5. So that part can cancel, and so I just have 6.98 cubed times 10 to the power 5. It has to come outside the bracket. Right, put that in the calculator. And what do we have? We have 4 pi squared. So 4 pi squared times 6.98 times to the power 3. 6.98 raised to the power 3 times 10 power 5. Oops. Yeah, you just got to watch out how you do that. Times 10 power 5 over 6.67 times 5.98. 6.67 times 5.98. And okay, that gives us a time or period of 5,801.6 seconds. So that's the answer. 5,801.62 seconds. Now we can convert that to minutes. Divide by 60. And we get 96.69 minutes. 6.69 minutes. And that should be the right answer at the back of the book. Right, so next question is question C. Show how the period of the new satellite can be determined without knowledge of the mass of the Earth. So in this case, we said that all satellites orbiting a common large body, that these two these two values will be constant. Right, so it's asking us show how the period of new satellite can be determined without knowledge of the mass of the Earth. So here we don't want to use the mass of the Earth. Right. Again, we're using that formula, this formula here, but we can't use the mass of the Earth. But that means we can't use this side of the formula. We're only going to use this side of the formula, knowing that these are constants for satellites going around a common body. So question D, that was B, or no, question C, sorry. So we're not using this side of the formula, right? So we're using the right hand side of the formula only, right? And we're saying this is going to be a constant. So you have a large body, it's the Earth this time, and you have a shuttle and a satellite. Different color. Right, so the shuttle's at 400 K and the satellite is at 600 K, and so the period, we know the period of the shuttle, which is given in the question. Go back to the question. So the period of the shuttle is 93. We use this. Right, so basically it is R1 cubed over T1 squared equals R2 cubed over T2 squared. Right, so we have R1 and we have R2, so we just rearrange this a bit. So we've got R1 cubed over R2 cubed, so we're just rearranging this, equals T1 squared over T2 squared. So we're after T2 in this case, which is the shuttle. Right, just rearranging this again. So T2 is going to be equal to the square root of T1 squared over R2, sorry, R2 over R1 all cubed. Right, now because there's a square root sign there, we can simplify this. It's going to be T1, and simplifying this, you're going to get R2 over R1 but we still need the square root of R2 R1. Right, so Okay, so at this stage we just can simplify a little bit further. Now you can put the values in straight away, but let's simplify it a little bit further, and so it's easier just to put in the calculator. You don't have to simplify too far. That'll do. And we have the values. T1 is the period of the shuttle, which was 93 minutes. Has to be in seconds. Convert it to seconds, multiplied by 60. Okay, radius 2 is, remember, the radius is from the center of the Earth to the satellite. Right, so the radius that we take when we're doing these calculations is from the center of the large body all the way to where the satellite is. That's the radius that we are talking about. So radius 2 is going to be the radius of the satellite. Radius 1 will be the radius of the shuttle. So radius 2 is the radius of the Earth. The radius of the Earth we can get we said the radius of the Earth over here. Okay, 6.38 times 10 to the negative 6. Six 0.38 times 10 to the negative 6, and the radius of the plus the distance where the satellite will be is 600k. Right, so 6 times 10 to the 5. And again, radius 1 is the radius of the Earth, plus how far away the shuttle is from the Earth. So 5, sorry. Right, 40,000 or 400,000 kilometers away, meters away, and that should be cubed. And we can put that straight into the calculator. But if you want to simplify it just a bit further, So 6.38 times 6. Oh, sorry. Sometimes if you simplify it too much, you can make mistakes. Sometimes it's better just to put it straight into the calculator. 98 times 10 to the 6 over 6.78 times 10 to the 6. Now we'll put it in. So we had 93 times 60. 3 times square root . Okay, we've got 6. 6. 6.78. So this is a new period. It's 5,828.71 seconds. So 5,828 should be similar to our previous period we calculated before, and it is not. We'll see why though. And we divide by by 60, and we get 97. Period 97. 7.414. Minutes. Now it's a bit different to what we had before. We had 96.69, and just have a look at the reason why. Right, so using this method to find the period, we get a time of 97.14 minutes, and the first in question B, it asked us to calculate the period also, and we got 96.69. So there's not much of a difference, basically. I think just rounding off error. So if you didn't have, the question says, if you didn't have the mass of the Earth, how would you calculate the period? Show how the period of the new satellite can be determined without knowledge of the mass of the Earth. So in this case, we didn't use the mass of the Earth to calculate the period. So that's what you have to do. Right, so knowing that these two formulas give us a constant value for all satellites going around a common body. So the last question D, if the new satellite was redesigned so that its mass was halved, how would your answer to question A change and question B change? So in question A, because we are using mass here, if it's halved, that means the energy would be half. And for question B, we're not using the mass of the satellite here to determine the period, so there'll be no change to question B. So for question D, the answers would be so question D. So for question A, for A, no change. Half. The energy would be half, because since you're using the mass. Okay, energy required would be half. Would be half. Or half the value that we calculated before, and B, there'll be no change because we're not using the mass to calculate the period. That's it. So that's it for satellites. So the main thing here is this formula, right? For satellites going around a common body, know that these two formulas will give you a constant value for all the satellites going around that large body. And That's it for satellite.